In fourth part for this magnetism and matter, we start with oscillation of a bar magnet. Here we are going to discuss the time period of oscillating bar magnet. Then in the picture, we come across two torques which are to be balanced. So in equilibrium, both the torques has to be equated. First is deflecting torque, then come to, so I talked about two torques. First is deflecting torque, tau 1 is I alpha, where moment of inertia of rectangular bar magnet and alpha is the angular acceleration. Then obviously in the process of this kind of horizontal oscillation, it will experience restoring torque as well. Then restoring torque, tau 2 is minus mbh sine theta, that is equal to minus mbh theta. This way we have got two expressions, 1 and 2. Therefore in equilibrium, tau 1 is equal to tau 2. It implies that this I alpha is equal to minus mbh theta upon I. I alpha is equal to minus mbh theta. It implies that alpha is equal to minus mbh theta upon I. And from here, alpha is equal to minus a theta. A is equal to mbh upon I. Now I'll first clarify the student who has forgot 11th physics SHM, then I'll be reminding, for any system to oscillate in SHM, there is condition for linear SHM. Linear SHM is acceleration A is directly proportional to Y displacement. Similarly, for rotational SHM, there should be the condition angular acceleration alpha should be directly proportional to theta. That means alpha is equal to minus k theta. That's what we have acquired here also, this k theta. And if you go further in previous step, alpha is equal to minus mbhi theta. That means here also it is in SHM. And therefore for SHM time period, t is 2 pi root under angular displacement, because y by a we used to have t is equal to 2 pi root under y by a. Now for angular SHM, angular displacement upon angular acceleration. Angular displacement is always theta. It implies that t is 2 pi. Here angular displacement was theta and angular acceleration is minus mbh theta by I. Here for root under purpose, we'll be ignoring this negative. The heading, some important terms related to magnetic properties of materials. Under this heading, we'll have first term to define and explain is magnetizing field, B naught. Now we'll have 4-5 terms very similar. The magnetic field, I'll keep on differentiating also among all the terms which we are discussing one by one, will appear similar, but there would be slight differences among all. Magnetic field that exists in vacuum and induces, this is B naught, because this field is particularly for vacuum, mu naught N I inside the solenoid in vacuum. Then here comes magnetic induction, Bm. Number 2, I'm referring this current. The above mentioned current for vacuum related field induces Bm inside the material. This gives rise magnetization surface current. Surface current Im. Therefore, Bm is mu naught N Im. The only difference between this expression and this expression B naught is equal to, this was the magnetic field for the same material in vacuum, but now if there is any medium inside the solenoid, then it would become Bm, and the expression would be mu naught Nim. Then in general, we have magnetic induction medium. From this language, you must be thinking on the line of flux, magnetic flux. Obviously, so you are right in thinking this way. Why? Since therefore B is phi B upon A, that's what this definition is talking about. Let's again repeat. Magnetic induction may be defined as the total number of magnetic lines of force crossing per unit area, normally through a medium. Flux is total number of magnetic field lines passing across any area normally, and area is that means per unit area. So this is general B, magnetic flux, and this is area. So this way is Tesla, only Tesla. So these were very general, but now very special has come. Number 3, magnetizing field intensity or magnetizing force or magnetic intensity, and this is H vector solenoid. This particular term is defined on the basis of solenoid or toroid. Toroid is solenoid wound over a ring. We have discussed already solenoid and toroid. This is toroid, solenoid, toroid, very rightly for solenoid or toroid. B naught is mu naught Ni, that is mu naught H. This is H vector, whose SI unit is ampere per meter. We can determine also through these formula. In this formula, H is equal to Ni. Therefore, H is Ni, and that can also be written as, from here, H is equal to B naught upon mu naught, here ampere per meter. So that was very easy to anticipate, but here you could notice magnetizing field intensity. Here we have intensity, फिर magnetic intensity, again intensity. But now next term which we are going to discuss, that is also intensity, but it is different, although dimensionally it is same. So we are entering into fourth, intensity of magnetization. Intensity of magnetization, I vector, and I is defined as magnetic dipole moment per unit volume of the magnet. So it implies that I is equal to m by v. For in support of this concept, I would like to draw. So this way we have got magnet. This is cross-sectional area A. Obviously, we would have pole strength also. Here we would have 2L magnetic length. Now what is left? QM. For that, south, QM, north, right? Then automatically, let's first m by v. I is equal to m by v, and further magnetic dipole moment would be written as 2L into QM, and volume, cross-sectional area into length. So cross-sectional area is A into 2L. 2L cancel, QM by A. Therefore, it should be all So magnetic dipole moment. Acha. I have already written. And volume of the magnet. This I have mentioned. Now we are going to discuss one very important formula, and it's 2-3 liner derivation. For that I am now creating some background. So intensity of magnetization. Finally, we'll have intensity of magnetization with reference to I is N IM. Now I need to explain magnetization surface current. And this is, and N is number of turns per unit length. Now IM is magnetization surface current. Therefore, considering whole of the discussion, now new point has arisen. Very exciting point. Resultant field inside. We experienced two types of fields. For vacuum, B naught. For medium, BM. So now we would be going for net field. Resultant field inside the material. B is equal to B naught plus Bm. And for B naught, we'll have mu naught H, magnetic intensity, and for Bm, it should be mu naught I. This I is intensity of magnetization. For our memory, I have mentioned. And this is Ni, ampere per meter. Here also ampere per meter. Therefore, B net is mu naught H plus I. 3, 4, and 5. This was 4, now 5. This is pura mu, such that mu is equal to mu naught into mu r. We won't require any language to support. Simply we should mention, since B is equal to mu h, therefore mu is B upon A. It is Tesla. It implies that Tesla meter per ampere. Whatever unit mu will have, same unit will be possessed by mu naught also. So this much is well sufficient. This is done. Then afterwards 6 mu r. Since mu is equal to mu naught into mu r, therefore r is mu upon mu naught. This is total and this is absolute. So relative permeability means relative magnetic permeability. It is a dimensionless number. We can see whatever dimension mu will have, same dimension of Tesla meter per ampere mu naught also will have. So hence it is mu r is dimensionless quantity like a dielectric constant, epsilon r or capital K in electrostatics. Here on the same line, all magnetic chapters we have mu r, and for air mu r is 1, and for steel mu r is more than 1000. Strong ferromagnetic substances will have in the order of 1000, 4000, 5000, this way. Last one, 7, chi m. It is defined as the ratio of I and H. That's why this is also dimensionless number. Ratio I by H. Chi, pronounced as chi. This is intensity of magnetization ampere per meter, and H is magnetic intensity. Again, this is also ampere per meter. Therefore, number which signify how magnetic temperament the material is possessing. Chi-m measures the ability of a substance to take up मैग्नेटाइजेशन, मतलब जितना ज्यादा काईएम का वैल्यू है वो उतना ज्यादा मैग्नेटिक फील्ड लाइंस को अपने अंदर भी खींचने की टेंडेंसी रख रहा है. एंड लास्टली रिलेशन बिटवीन मैग्नेटिक permeability and magnetic susceptibility. Already basic background we have created. We have been just in above paragraphs. I'm reminding we came across one discussion. Yeah, as you can see here, B net is equal to mu naught H plus I. From here, we'll be proceeding. B net from above discussions for any linear magnetic material when is subjected to magnetizing field intensity, H vector develops magnetization I and magnetic induction B, then B is equal to mu naught H plus I, because in books you may find M, but I prefer writing I for intensity of magnetization. Since B is equal to mu H, it implies that mu H is equal to mu naught H plus I, and also mu is equal to mu naught into mu R. So mu R is mu upon mu naught. Then we can replace mu upon mu naught is equal to H plus I upon H. It implies that mu R 1 plus I by H, and I by H is chi m proved. And here this was chi m. Let us again see. Already we have had this discussion. Then afterwards we'll be having, as far as I remember, Curie law, hysteresis curve, and comparison of steel and soft iron core. That's all. That much is left. This is the relation between, this is magnetic susceptibility, and this is relative permeability. Again, while proving B is equal to mu H and mu is equal to mu naught into mu R. So mu R is mu by mu naught, and this thing we have utilized over here, from here to here, and this is H upon H 1 and I by H chi m. So hence the relation is done. Mention two relations more. What is that? Basically, these are two important conversion factors for H, that is magnetic intensity. 80 ampere per meter is equal to 1 oersted. And if you remember, oersted is CGS unit for measuring H vector, that is magnetic intensity. I'll again, this is CGS, this is SI for H vector, where 1 oersted is equal to 1 Gauss upon mu naught. This way we have discussed one very important conversion factor related to H vector, of course. Then here comes, so our next topic would be Curie's law in magnetism. But for studying Curie's law, we need to first have some introductory knowledge related to classification of magnetic materials. That is, magnetic materials are of three types, basically diamagnetic, paramagnetic, and ferromagnetic. So we must have basic and primary definition for these three. Let's first classification of magnetic materials. First, number one, diamagnetic. These substances develop feeble magnetization in the opposite direction of the magnetizing field. These substances are feebly repelled by magnets and tend to move from stronger to weaker parts of a magnetic field. Now, what about paramagnetic? Number two, these substances develop feeble magnetization in the direction of the magnetizing field. They are feebly attracted magnets and tend to move from weaker to stronger parts of the magnetic field. And lastly, ferromagnetics. These substances develop strong magnetization in the direction of the magnetizing field. They are strongly attracted by magnets and tend to move from weaker to stronger part of a magnetic field. Example, iron, cobalt, nickel, gadolinium. Now here comes Curie law, and this is for paramagnetic material. This is only for paramagnetic material. Experimentally, it was found that the intensity of magnetization I of the paramagnetic material is first directly proportional to the H vector magnetizing field intensity, and number two, I is inversely proportional to the temperature, absolute temperature. Therefore, I is proportional to H by T. Imply that I by H is inversely proportional to temperature. It implies that chi m is equal to C by T, susceptibility of the material, and this is Curie constant, and this T is absolute temperature, and this is graph I versus H by T, Curie law region, and this is saturation. Beyond the saturation value ms, Curie law is not valid. Right. Now here comes modified Curie's law for ferromagnetic substances. After discussing Curie's law in magnetism, this was for paramagnetic substance. Now, modified Curie's law we are to discuss for ferromagnetic substance. So let me first give the heading modified Curie's law for ferromagnetic substance. Under this heading, we need to refer one temperature, one specific temperature, that is called Curie temperature or Curie point. Let's discuss this first. And for your information, again, I wanted to mention the basic difference between diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic substances does not support magnetism, whereas Paramagnetic substances support external magnetic field in which it is kept, and ferromagnetic strongly support external magnetic field in which it is kept. Then now I was to refer Curie temperature or Curie point. The temperature at which a ferromagnetic substance becomes paramagnetic, called Curie temperature or Curie point Tc. That means at this particular temperature, ferromagnetic will become paramagnetic. That means there is huge loss of very big characteristic related to magnetism as we increase temperature for any magnetic material. Now I'm to underline Curie temperature or Curie point. Above the Curie point, that is paramagnetic phase, the susceptibility, that is chi m, varies with temperature as. And again, let me remind Curie's law original. That was susceptibility equals C upon T. That means susceptibility was inversely proportional to temperature, absolute temperature. Now let us compare. Here we have C dash T minus Tc, where T is greater than Tc. We need to remember C dash is a constant, Tn Tc. Tc was Curie temperature or Curie point, and T is absolute temperature. The above law for ferromagnetic material above the Curie's temperature is known as Curie-West law. Statement for this law: statement, the susceptibility of a ferromagnetic material above its Curie temperature is inversely proportional to the axis of temperature above the Curie temperature. That means, in plain language, chi, that is susceptibility, is inversely proportional to the difference between both the temperature. That's what mathematically we have here. This denominator T minus Tc is that difference only, which is now talked in the statement. Axis. This axis is that difference only. Of course, ferromagnetic inversely proportional to the above the Curie temperature. This way, we had two Curie's law. Both we have discussed. Now, here comes comparison between dia, para and ferro. After completing both the two laws related to Curie temperature and Curie thing, already we have discussed Curie law for paramagnetic and ferromagnetic both. Then here comes, before doing Curie law, I discuss very small comparison between dia, para and ferro. Actually, now I am to cover up thorough comparison between these three types of magnetic materials. So for your purpose, already I have arranged very important screenshots. Some I am to discuss here, and some more I will be sharing while doing video editing. So let us come to these 4 screenshots first. Here, firstly, behavior. In context of behavior in non-uniform magnetic field, how these 3 types of magnetic materials behave. It moves from stronger to weaker magnetic field. See, north and south pole strength. Diamagnetic substances are going away. It completely went away from pole strength. Whereas paramagnetic, now see, they have accumulated towards pole strength, very close. Then ferromagnetic, strongly they have approached towards pole strength. Then this was weak field, now strong field. Again they went away, strong field, they have accumulated near to stronger field, and here stronger accumulation because of ferromagnetic. Then after that, when we have any diamagnetic liquid in U tube, then this diamagnetic liquid will have tendency to go away from the stronger field, whereas for paramagnetic substances, now this liquid is approaching towards stronger field, right? Then chi-m T curve, that means graphical analysis. Criteria of comparison is graphical analysis between susceptibility to temperature. For diamagnetic, it is simply straight line, that means it is independent. Here for paramagnetic substances, susceptibility is inversely proportional to temperature. We have already read this law under the heading Curie law for paramagnetic. Then for ferromagnetic, again chi-m is inversely proportional to temperature only, provided this TC line is the barrier. That means इनसे कम में तो कुछ भी गुजारा है ही नहीं. During in this region there is no variation beyond this TC only, this analysis. And remember, this T is absolute temperature in both these situations, and TC was Curie temperature. Now fourth parameter, that is relative magnetic permeability. For diamagnetic, it lies between 1 and 0, right? मतलब 0 से ज़्यादा ज़रूर हो लेकिन 1 से कम. Here for paramagnetic substances, permeability lies between 2 and 1, and here relative magnetic permeability is very large as compared to 1. Why? Because it has to demonstrate strong responses towards external magnetic field in which ferromagnetic substances are kept. For example, copper, nickel, cobalt, they have mu r in the order of 1000, 2000, 3000, 4000, like this. Then fifth parameter, magnetic moment of single atom. Atoms do not have any permanent magnetic moment. This magnetic moment we discussed under the heading Bohr magneton. If you remember, we analyzed mathematically that capital M is 1 by 2 e omega r square, right? If you want, I can show you, but this we covered in third video. We may not be able to access here. Yeah, we can't have, because fourth video we started with. For the time being, you remember. And so in context to that only, atoms do not have any permanent magnetic moment, whereas atoms have permanent magnetic moment which are randomly oriented. That is for paramagnetic. And ferromagnetic, again permanent magnetic moment which are organized in domains. And next parameter, when rod of material is suspended between poles of magnet, diamagnetic substance will be aligned like this, perpendicular. That means they are not to support this strong magnetic field, whereas paramagnetic will be aligning along this magnetic field. And here ferromagnetic will be strongly aligning. Then next, magnetic moment of substance in presence of external magnetic field. Value M is very less and opposite to H. Okay, and here value M is low but in direction of H. H means magnetic intensity or magnetizing force or magnetizing field. All the three are for same. M is very high. For diamagnetic, M was very less. For paramagnetic, M is low but in direction of H. But here M is very high and in direction of H. And these are the examples. You can note it down for your reference. Interesting part is iron, cobalt, nickel, all their alloys, and then this GD is gadolinium and this is alnico. So these are important. And second last, substances placed in uniform magnetic field. How do they respond when they are placed in uniform magnetic field? Here in case of diamagnetic, they prefer not to let them enter. All these field lines are trying to go outside. But for paramagnetic, a lot of magnetic field lines will be trying to enter through the paramagnetic while it is passing through the paramagnetic substance. And ferromagnetic में क्या होता है? They behave very friendly. All the field lines are trying to go and pass through the ferromagnetic substance only. They prefer not to go out. All the lines will try to enter through the ferromagnetics. And last, IH curve. I means intensity of magnetization versus magnetic intensity. Small negative varies linearly with field. This shows the graph is in fourth quadrant. It shows it is negative but linear variation. But for paramagnetic, it is linear variation only but positive. What we could conclude? Negative, that means they behave negatively towards external magnetic field, whereas paramagnetic behave positive, and ferromagnetic, they behave exponentially. That means they are to respond very positively towards external magnetic field. So in general, we have discussed all. Even then, I'll be sharing few more screenshots when you will be going through the video. So very slight discussion. What is hysteresis? Hysteresis, let us first know what is, in terms of definition, what is hysteresis. Basically, hysteresis is the variation of B and H. It is the variation of B and H. B, that means magnetic field induction. H means magnetic intensity. All together for any magnetic sample when it is subjected for magnetization and demagnetization. And what's the definition? Phenomena of lagging of I or B behind H. You won't be able to understand this language of definition unless and until I draw the diagram, total graph. So wait for a while. I'm reaching behind H when a specimen of magnetic material subjected to a cycle of magnetization is called hysteresis, lagging of I or B behind H. Now this is H max. This was H ampere per meter. This was here B. That means Tesla. This is H max. From the diagram, you could very easily observe that as H increases, B also increases, but proportionately, as H increases, B could not increase at that speed. That means something is lagging. Otherwise, graph could be like that also. But intentionally, variation became curvy, and because of this curvy thing, in definition, we had phenomenon of lagging of I or B behind H. मतलब late चल रहा है. Whether we consider I or B along y axis and H along x axis when a specimen. So basically this whole graph is graphical variation between B and H, magnetic field induction and magnetizing force or magnetic intensity, right? And when any magnetic material is subjected to magnetization and demagnetization, this whole graph talks about the cycle of magnetization and demagnetization. That means, see, it is a process of, as my cursor is going, this is process of magnetization. Here, now demagnetization process begin, and it will be going till this point. Then after that, again magnetization process starts. So this whole thing is studied under this graph. Now I am to discuss two physical quantities, namely residual magnetism or retentivity, right? So for this, I must mention the definition: retentivity or residual magnetism. Residual magnetism means bacha kucha hua. So in the graph, I'm going to show you what is that bacha kucha hua. Residual और रिटेंटिविटी, रिटेन करना. तो ये अभी तक आपका मैग्नेटिक मटेरियल ने मैग्नेटिज्म, अमाउंट ऑफ मैग्नेटिज्म और मैग्नेटिक फील्ड को रिटेन किया हुआ है. व्हाट इज दैट? दिस बोल्ड ब्लू लाइन इज रेसिडुअल मैग्नेटिज्म और रिटेंटिविटी. रेसिडुअल मैग्नेटिज्म, how do we define? The value of magnetic induction be left in the specimen when the value of magnetic induction be left in the specimen when the magnetizing force is reduced to zero is called retentivity of the material. Now I am going to explain in the graph. Let's see what our language says. The value of magnetic induction be left in the specimen when the magnetizing force is reduced to zero is called retentivity. Let's come to the graph. See, now if we want to decrease this H to zero, so let's see how variation proceeds as this graph is proceeding. Finally, at this point where my cursor is static now, H has become zero, and at this position still this much B is left. That means in absence of any cause of external magnetic field, still our magnetic sample consist of this much magnetic field. Even we have removed our source of external magnetic field, there might be some strong magnets which we have removed for now. That's why H has become 0. That is residual magnetism, and for that only I have mentioned the definition. So this was our keyword, magnetizing force. That means H is 0. Then here comes coercivity. For coercivity also, now if we want to decrease this B also to 0, then we need to apply from external source, external magnetic field in opposite direction. So this was positive H. Now negative H we need to impose, and this much negative H is needed for decreasing this B to 0. Now which color I should? This green is coercivity. That means negative value of H needed for decreasing this B to 0. Now proper definition for coercivity. Value of magnetizing force in opposite direction to reduce the residual magnetism to 0 is called the coercivity. Negative H to reduce the residual magnetism to 0. Then one more, energy dissipation due to hysteresis. Energy dissipation during hysteresis. Basically this topic is similar to the resistor. When any current is made to pass through the resistor, then resistor offers some resistance, and because of that resistance, because of that obstruction, heat is dissipated across the resistor. Same way, when any magnetic material is subjected for magnetization, then it also offers some resistance towards magnetization. Then during magnetization, some negligible amount of heat is dissipated, and during demagnetization, obviously heat should be absorbed. So that is the point. Now I'll be associating this fact while comparing soft iron and steel. That means electromagnets and permanent magnet. Area of hysteresis loop is equal to the energy dissipation during magnetization, and comparison of steel and iron. Iron means soft iron we have to think for. Now very interesting, steel will have fat and bulky hysteresis loop. Why? And iron will have very thin, slim and trim. This is what's the significance? Fat and bulky. What's the significance behind this? Mu for soft iron, and this is steel. For soft iron, mu r is maximum. That means whenever this material is kept in uniform magnetic field or external magnetic field, it absorbs maximum number of field lines more effectively, vigorously, without any effort. So that means it is offering least resistance towards magnetization, and since it is offering least resistance, that's why energy dissipation will be also very less. That's why very slim, trim and thin. Whereas on the other hand, for steel, its mu r is not that much high, so it has to offer great resistance towards magnetization. Hence it will be dissipating great amount of heat as compared to soft iron, thereby fat and bulky. And that is the reason steel is used for permanent magnets, whereas soft iron core is used for electromagnets. So I'm going to paste one screenshot having comparative study between permanent magnets and electromagnets also. That means what are the characteristics needed for permanent magnets and electromagnets respectively. For that question purpose, you may learn that table. Hence, our discussion has to be ended here only. Thanks for viewing and enjoying my video. Keep on working. All the best. See you in next video. Bye. Take care.